Learning goals. Welcome to this learning session on binomial distributions and probability. In this course, we shall address Introduction to Binomial Distributions, Binomial Notation and Golden Rules, Binomial Formulae and Coefficients, Worked Examples, Probability and Mean, Practice Problem. There will be a quiz at the end to test your knowledge.
Introduction to Binomial Distributions. When dealing with a small number of trials, probability tree diagrams are an effective way to visualize and calculate probabilities. However, as the number of trials increases beyond 2, these diagrams quickly become complex and unwieldy, making calculations cumbersome and prone to error. For situations involving a larger fixed number of independent trials, the binomial distribution offers a more efficient and systematic approach. It allows us to determine the probability of a specific number of successes in a sequence of trials, where each trial has only 2 possible outcomes. This method simplifies the process significantly, moving from a visual, branching representation to a more algebraic calculation. For instance, calculating the probability of 7 heads in 10 coin flips would be impractical with a tree diagram, but straightforward with binomial distribution. Binomial expansion formulae. The core of binomial distribution relies on the binomial expansion of p plus qn, where n represents the number of trials, p is the probability of success, and q is the probability of failure. Each term in this expansion corresponds to the probability of a specific number of successes. For a small number of trials, such as 3, 4, or 5, the expansions are readily expressed. For example, p plus q4 expands to p plus 3p plus 3, where each term represents the probability of 3, 2, 1, or 0 successes, respectively. It is important to note that these specific formulae do not need to be memorized for exams. Typically, any necessary formula or the general form will be provided in the question or within a formula sheet. The key is understanding how to apply the expansion rather than recalling its exact terms. Interestingly, the coefficients in these binomial expansions, such as 1, 3, 3, 1 for p plus q, are directly derived from Pascal's triangle. Each row of Pascal's triangle provides the coefficients for a binomial expansion of a certain power, offering a visual and systematic way to generate them. Calculating binomial coefficients. To find the coefficients for any term in a binomial expansion, especially for larger values of n, you can efficiently use the combination function, denoted as NCR, on your calculator. This function calculates the number of ways to choose R successes from n trials without regard to the order. For example, to find the coefficients for the expansion of p plus q, you would use n equal 5 and vary r from 0 to 5. This means calculating faf c0, faf c1, c2, c3, fem c4, and venc cc. These calculations yield the coefficients 1, 5, 10, 10, 5, and 1, respectively, which are the same numbers found in the 5th row of Pascal's triangle. Understanding the NCR function is crucial because it directly relates to the number of different paths that lead to a specific number of successes in a probability tree. For instance, C2 equals 10 means there are 10 distinct sequences of 2 successes and 3 failures in 5 trials. Binomial distribution notation, BNP. The notation BNP is used to formally denote a binomial distribution. Here, E represents the fixed number of independent trials, and P signifies the constant probability of success for each individual trial. This concise notation encapsulates all the essential parameters of a specific binomial scenario. For any binomial distribution BNP, the probability of failure for a single trial is denoted by Q, which is simply calculated as 1 minus P. This relationship ensures that the sum of probabilities for success and failure in any given trial always equals 1. The probabilities for the various events of n binomial trials are directly given by the terms of the binomial expansion, p plus q. Each term corresponds to the probability of achieving a specific number of successes, from 0 up to n successes. A key characteristic of the binomial distribution is its mean, which represents the expected number of successes over n trials. This mean is easily calculated as the product of the number of trials and the probability of success, expressed as NP. For example, if you flip a fair coin 100 times, the expected number of heads, mean, is 100.5 The binomial distribution relies on specific rules to accurately model probabilistic situations. Understanding these golden rules is crucial for appropriate application. The first rule is that the number of trials, denoted by n, must be fixed and predetermined before the experiment begins. This ensures a clear scope for the probability calculations. Secondly, each trial must be independent of the others. This means the outcome of one trial does not influence the outcome of any subsequent trial. For example, flipping a coin multiple times is independent, but drawing cards from a deck without replacement is not, as the probability changes with each draw. Finally, there must be exactly two possible outcomes for each trial, a success or a failure. These outcomes must be mutually exclusive and exhaustive. This binary nature is fundamental to the binomial model, distinguishing it from other probability distributions that handle multiple outcomes. Adhering to these three conditions ensures that the binomial distribution is a valid and accurate model for the given probabilistic scenario. If any of these conditions are not met, a different probability distribution, such as a hypergeometric or multinomial distribution, might be more appropriate. Worked example: spinner probability. Let's apply the binomial distribution to a practical example. Imagine a spinner where the probability of landing on blue is 0.4. If the spinner is spun 4 times, we want to determine the probability of specific outcomes. This scenario fits a binomial distribution B4 0.4, where n equals 4 trials and p equal 0.4 probability of success, landing on blue. Consequently, the probability of failure, Q, is 1 minus 0.4 equals 0.6. To work out the probability of landing on blue exactly 2 times, px equals 2, we use the term from the binomial expansion, p plus q plus forward, that corresponds to 2 successes. This term is 6p kickwords for 4. Substituting the values, we get 6.4 forward, 6 0.16 to 0.36 is 0.3456. This calculation directly gives the probability of exactly 2 successes in 4 trials. Now, consider the probability of landing on blue more than 2 times, px greater than 2. This means we are interested in either 3 successes, x equals 3, or 4 successes, x equals 4. Since these events are mutually exclusive, we can add their individual probabilities. The term for x equals 3 is 4pq, and for x equals 4 is before. Calculating these, px3 equals 4 0.4 0.6 equals 4 times 0.6 equals 0.1536 equal 4 is equal to 0.4 true equals 0.0256. Therefore, px2 px4 equals 0.1536 plus 0.256 0.1792. This demonstrates how to combine probabilities for multiple outcomes in a binomial distribution. Worked example: mean number of successes. Beyond calculating specific probabilities, the binomial distribution also allows us to estimate the mean, or expected, number of successes over a larger series of trials. This is a very useful measure for understanding the overall trend of outcomes. Using the spinner example, where the probability of landing on blue P is 0.4, we can estimate the mean number of times the spinner will land on blue in 100 spins. The formula for the mean, Ex, of a binomial distribution is simply NP, where n is the total number of trials. In this case, with 100 spins, n equal 100, and a probability of success of 0.4, p equals 0.4, the estimated mean number of times the spinner will land on blue is 100 times 0.4 equals 40. This means that, on average, we would expect to see 40 blue landings out of 100 spins. This concept of mean is widely applicable in various fields. For instance, if a quality control process checks 500 items with a 2% defect rate, the expected number of defective items would be 500.02 equals 10. This provides a quick estimate for planning and resource allocation. Practice problem, SUV probability. Now let's test your understanding with a practice problem. On a road near Ken's house, the probability that any car passing is an SUV is 0.15. We are interested in the number of SUVs in the first 5 cars that pass. Let x be this number. First, work out the probability that all 5 cars are SUVs. This requires applying the binomial probability formula for equal 5 using n equal 5 and p equals 0.15. Remember that q equals 1 minus p. Next, calculate the probability that at least 4 cars are SUVs. This means finding the probability of x equal 4 plus the probability of x equal 5. You will need to calculate each of these probabilities separately and then sum them. Finally, estimate the mean number of SUVs for the first 500 cars that pass Ken's house. This involves using the mean formula EX equals NP with the new total number of trials.
Summary. Well done, you have completed the course, Binomial Distributions and Probability. You should now be familiar with Introduction to Binomial Distributions, Binomial Notation and Golden Rules, Binomial Formulae and Coefficients, Worked Examples, Probability and Mean, Practice Problem. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen.